Pressure and delta G. Enthalpy, or delta H, is not affected by pressure. Entropy, or delta S, is dependent on pressure because entropy is dependent on volume. A large volume has more disorder or entropy than a small volume will. Low pressure has more disorder or microstates than a high pressure would. Delta G in equilibrium. The equilibrium point occurs at the lowest value of free energy available to the reaction system. This means that a reaction may not reach completion, but instead reach equilibrium, even if it has a really negative delta G. A is where it's starting and B are the products. So in this first analogy, when the ball rolls down the hill, it goes from A to B, or from the reactants to the products. No issues. This would be like ice melting. It's ice, and then it's melting, and now it's a liquid. All of it's turned into a liquid. But in the second analogy, we have, here's our reactants, there's our products. But as the ball goes down, it never reaches the products being fully completion, because we're going to reach equilibrium at C. C is the lowest point of energy, so therefore the reaction stops there at equilibrium before going on to completion. We have delta G naught is equal to negative RT ln K. Our delta G naught is equal to negative Ratlink. This helps us determine, knowing the delta G value, what is our equilibrium constant, or K. If we have a really large K, then that means our reaction will go to completion. If we have a smaller K, then our reaction is not going to go to completion. When delta G naught is 0, the system is at equilibrium. K is equal to 1, the pressures are all at 1 atm, and Q will equal K. When delta G is less than 0, aka negative delta G, the system is not at equilibrium. Our K should be greater than 1, and our Q will be greater than our K, because we should have more products than reactants. Our product should be greater than 1 atm, our reactant should be less than 1 atm. Therefore, the reaction will shift right to create more products. When delta G naught is greater than 0, or delta G is positive, the system again is not at equilibrium. K is going to be less than 1. Our Q will be less than K because we have more reactants than products. So reactants are greater than 1, products are less than 1. So the reaction shifts left to make more reactants, to bring our value of Q equal to K. Another reaction that we can use is this equation here, which is referred to as the Nernst equation. You do not need to solve for the Nernst equation on the AP test, but you do need to be able to understand it qualitatively. And as of now, the Nernst equation is on the formula chart. We have delta G. Notice there's no little naught on it, naught being that O. So delta G without that naught means that it occurs at whatever specified pressures for reactants and products, while delta G naught has to be at 1 atm. When we're using our delta G's of formation or solving for delta G using Hess's law, that's always going to be delta G naught. To get delta G when you're not at standard pressure, that's when we have to use this equation to solve for delta G. R is a gas law constant, but for our gas law constant, we have to use the gas law constant that has joules in it, which was the kPa one, 8.314 joules per Kelvin times moles. Again, this constant is on your formula chart. T is temperature, and it must be in Kelvin, and Q is our reaction quotient. It's the same reaction quotient that we've seen in the equilibrium unit, since we are relating Q to K, which is related to our delta G. And so it's going to be products over reactants is equal to my Q. Just like before, we'll eliminate all solids and liquids from our Q expression. One other thing to note is notice that our delta G is normally in kilojoules, but our R is in joules. You need to make sure that you convert your delta G to joules or your R to kilojoules before plugging them in. So let's see how we could use the Nernst equation to figure out which way a reaction will shift to reach equilibrium. From the previous slide, our equation is delta G equals delta G naught plus RT ln Q. They gave us the delta G naught. And so delta G is equal to negative 33.3 kilojoules plus R. We need to make sure that we convert R to kilojoules, so 0.008314 times temperature in Kelvin, and then ln Q. For our Q, we're going to do products over reactants, so NH3, the pressure of that squared over N2, and then H2 cubed. So our NH3 was 1, so that cubed over 1.47, and then 1 times 10 to the negative 2 cubed. Solving all of that out, we get 680272. So 680272. So delta G is equal to negative 33.3 plus ln of that times 298 times 0.008314. We get 33.3. Well, negative 33 plus 33, delta G is equal to 0. So we're at equilibrium, so no shift will occur. Go ahead and pause the video if you need to. Otherwise, we're going to look at B. On B, we're going to do the same thing. But this time, when I solve for Q, I have 1 squared over 1 times 1 cubed is equal to 1. So if I plug in ln of 1 is 0. 0 times anything is going to give me 0, so this whole thing is 0. Therefore, my delta G is equal to my delta G naught, which is equal to negative 33.3 kilojoules. Since I have a negative delta G, my reaction should shift to the right. Without solving it, we could have figured that out because delta G naught means I'm at standard conditions. Standard conditions are 25 degrees Celsius and 1 ATM for everything. Since I had standard conditions, my delta G should equal my delta G naught. On this problem, we're just trying to calculate our equilibrium constant. So we're going to be using delta G equals negative Ratlink. But they didn't give you the delta G. They gave you delta H as a formation and delta S as a formation. So we need to use this equation to solve for our delta G. Before we can do that reaction, though, we need to figure out our delta H by doing products minus reactants and doing finding our delta S by doing products minus reactants. So step 1 is we need to find these. Then I'm going to find delta G, and then I can find my K value. So go ahead and find your H and S and restart once you have your H and S. So for H, you should have got a negative 1652 kilojoules, and for delta S, negative 543 joules times Kelvin times moles. Go ahead and solve for delta G now. Restart when you have your delta G. So for delta G, make sure that you converted your delta S to kilojoules. And then plugging it in, I got negative 1490.2 kilojoules. And finally, let's calculate delta G, or calculate our K value. So calculate K. Restart when you have your K value. So for our K value, you should have converted either your kilojoules to joules for delta G or your R to kilojoules. This time I went ahead and converted my R to kilojoules. And the temperature, it was 25 degrees Celsius, so that's 298. So I do 1490.2 divided by the product of negative 0.008314 times 298. And that gives me 601.48 is equal to ln of K. To get K by itself, I need to get rid of ln, and the opposite of ln is raising it to the power of e. E to the 601 is equal to K. When I try to type that in the calculator, it gives me an overflow error because the value is too large. So I'm going to leave it as this because, again, of that overflow error. If it had given me a number, then I would type that number in. Notice that this K is very, very large, so large that, again, the calculator can't even compute that. And so this reaction is going to completion. So this one, we're just looking for the equilibrium constant. And to make it much easier, I've already given you the delta G. Notice that it says that we're at delta G naught. That always means that we're at 1 atm and 25 degrees Celsius. So the temperature is 25. Go ahead and pause the video and try this one on your own. Restart when you have your equilibrium constant. So we had 50.2. We need to divide by negative 0.008314 divided by 298 gives us negative 20.26 is equal to ln of K. Just like before, I'm going to say e to the negative 20.26 is going to equal my K, which in this case is 1.59 times 10 to the negative 9th. Notice that this K is much smaller. This reaction will definitely be reaching equilibrium, not completion. So delta G, or free energy, is telling us how much work can be done with a given process. A negative delta G means the amount of free energy available to do or to use as work. While if you have a positive delta G, then that value is the minimum amount of work that must be expended to make a reaction occur. The amount of work that we actually obtain from a spontaneous process or a thermodynamically favored process is always less than the maximum amount possible, though. If we had a delta G of negative 50 kilojoules, we don't actually have 50 kilojoules of work available, or we're not going to be able to do 50 kilojoules of work because we're going to lose some of that energy in different forms, such as friction or heat to the surroundings. For example, when gas is burned in a car's engine, only about 20% of that maximum work available is actually used. So here we have 3 delta G's. Which one would occur the fastest? Go ahead and pause the video and select your answer. If you said D, you're correct. This is fastest. And delta G doesn't give us any information about kinetics. Delta G only tells us which one of these is spontaneous or thermodynamically favored. So this one is thermo-favored and should occur without any outside intervention, but it doesn't mean that it's going to occur fast.